recording. So now we have backup. One for live presentation and one as a backup. All right, so we can go back to 440. Uh, and I lost that. Well, I mean, this is good enough, as a starting point. Okay. So resuming our discussion of the prepositional logic system thing, um, we have three components. Okay, I hope you guys had a chance to review the material before class today, because we had a long spring break with one day after spring break coming back, and then another break, short break again, of for this Monday. So, I don't really like, time to be kind of scattered like that. So we have three components. The first component is resolution. So let me go back to the slide on resolution. So the idea of resolution is when we perform resolution, we are losing things. Okay. In other words, if the original expression is an and, each side of the and is a or, and one side of the and has a or that has some expression psi, and then the other one has the negation of that psi. If this is how things are set up, then this entire conjunction implies this disjunction here. But you can see that in the original conjunction, it has three expressions. It has phi, it has psi, it also has rho. But in the resulting thing that it is implying, we only have two things. Out of the three, psi is gone entirely. In other words, the repeated application of resolution will only make things simpler and simpler and simpler until you get false. In other words, okay, let me give you the scenario where you get false. So let me use, I think Joplin is good for this purpose. So I'm going to start up Joplin here. Joplin, there we go. All right, so here's Joplin, and I'm going to start a new date, okay, just so that it's slightly better organized. New note, and name that after today's date, 0402. Ooh, look at that. Just zeros and twos and fours in today's date. Oh, is it five already? Ah, darn. Okay. We have to convert to use star date. It really does not make sense. The way we allocate number of days in a month, it's like, why? I don't know. Why are there 7 days in a week? Well, I kind of know the reason of that, but I would still say that is not logical. Yep. It doesn't make it invalid. It just makes it illogical. That's all. Or just count the number of days in a year. Do not bother to have months. Months are supposed to be coinciding with the cycle of the moon. So that I can see how it makes sense. But you know, anyway. All right. So we need to talk about resolution. So if I have two variables, so I'm only using the simplified form, at this point. So if we have p or not q and q, excuse me, not p or not q, the whole thing, and q or s. Okay, using resolution, now we can say this implies p or s. Okay, so can everybody see how I just applied um, resolution? But this time, every component is just either a variable or the negation of a variable. So are we good with this? Okay. So now we can say, what if we have something like this? What if instead of P, we have just false? So false or not Q, it's just not Q, right? Because false is the identity of disjunction, which means it's kind of the same thing as actual plus, right? Zero plus whatever is just whatever. So on the other side, we have Q, or guess what? The identity of or. So now you go like, okay, syntactically, I can see how this would just become false or false, which is false. Do we all agree that false or false is just false? Okay, so that means if we apply resolution repeatedly, there's a chance that we can make the whole thing imply false. Does that make sense? If we have a long chain of the application of resolution, each time we are getting rid of something and then concatenating the rest of the disjunction together. So that means we keep losing things and eventually we lose everything. And once we quote unquote lose everything, we just have false left. That is the only thing left in the disjunction. Is that okay? Is that concept okay? All right. So that's one. Resolution is one concept that is important in this entire discussion. The second concept that is also really important in this discussion is in order to apply resolution, it would be nice if we start off with a conjunction of a whole bunch of disjunctions. Does that make sense? Because this is the format in which resolution can work with. Resolution does not work with implication. It does not work with a disjunction of conjunctions. It does not work with anything else other than something of this form. So now we move on to CNF. So CNF, conjunctive normal form, which is something that we talked about last Wednesday, is basically saying if you give me any Boolean expression, and we talked about how to randomly generate an expression for practice purposes. Do you guys still remember that approach? Okay, so it is basically an approach to choose an operator, when you're constructing the tree that is the Boolean expression, and every time you have a choice, you can choose one of the operators. We have implication, disjunction, conjunction, and negation. And then we have a fifth option, which is, oh, let's just make this a variable instead of an operator. So we have five choices to choose from, and then you just kind of construct, you just recursively construct the expression. You can always say, I want to have at least two levels of operators before we get to the variables. Fine, make it, make it so. Okay. And then when we get to the variables, you once again have a choice because we have PQRST as variables. So once again, throw a dice, randomly pick one of the variables. The whole idea is we just need a semi systematic way to generate expressions so that we can test our approach on the expression. So that's what we talked about last time. So CNF, conjunctive normal form, is basically redefining what is well formed. Before, we have a kind of general sense of what is well formed. As long as each operator is given the right number of operands and each operand itself is well formed, then the whole thing is going to be well formed. So that's really nice in the sense that, oh, we can now represent every Boolean expression that we can think of. But from the perspective of not resolution, but from the perspective of the transformation rules, it also means that we can end up with a lot of expressions that are basically useless. Okay, so the new definition of what is well formed is basically saying a Boolean expression that is well formed can only be a disjunction of something. Okay, there's no conjunction anymore. And inside the disjunction, you can only have either something that is from alpha or the negation of something from alpha. So that is the new restriction of what is considered to be well formed. So somebody gonna say, but where's conjunction? Conjunction is implied. Everything that is known to be true or is derived to be true are all ended together implicitly. That's where the conjunction is. In other words, if you look at all the expressions that are labeled, including the ones, starting with the ones that are in iota and also the ones that are derived, they are basically all ended together. And therefore, we have a CNF, a conjunctive normal form, a and of a bunch of ors. So is that okay so far? All right. So the derivation from any general expression into CNF is somewhat mechanical. I illustrated one example last time, and I can illustrate another example this time also if you guys want me to do that. So that's the second component. The third component is proof by contradiction. Okay, so now let's take a look at contradiction, proof by contradiction. This is something that we talked about last Wednesday. So this is a corollary of proof by contradiction. Basically, we're saying that if P implies Q is true, then we can add a conjunction with R on both sides of the implication. The resulting implication is also guaranteed to be true, no matter what you choose as the R. Is that okay? And this one is proven by a bunch of Boolean algebra. So this is one way to give you some exposure to Boolean algebra and how it can be applied. So the bottom line, okay, the bottom line is this implication is always true. So now we try to use this corollary to prove that proof by contradiction is valid. Yes. Okay, what did I just say? And what did you mean what did you think I mean by that? I said this is a proof that proof by contradiction is valid. It is a valid way to prove theorems. That is what I said. Yes, go ahead. Vaguely, yes. So to be more precise, okay, you are given two things. You are given psi, okay? Psi is everything that is axiomatically true. In our discussion, psi would be a conjunction of everything that is in iota. Is that okay? So because iota, every expression is iota in iota is true by definition, axiomatically. So we don't ask why are they true. We just say that these things are assumed true to begin with. So that is represented by psi here. Phi, on the other hand, is another Boolean expression, and that we want to find out, is it implied by psi? Because if phi, in fact, is implied by psi, then phi is called a theorem of psi. That is how we define what a theorem is in this class, and also in basically all your math classes. So I'm going to pause right now, okay, and see if there are any questions about, what a theorem is and what do we need in order to prove a theorem. Do we have any questions about those more abstract, topics, mostly about, the terms, and what each term means? So do we have any questions about that? Yes, go ahead. In general, a theorem is a statement that is implied by things that are axiomatically true or given to be true. So can you have a chain of implication starting with everything that is known to be true to arrive to the thing that you suspect is a theorem, but it's not necessarily the case. You do not make any assumption. You simply ask, is this implication true? This is given to you already. This is what you need to see whether it's a theorem or not. You're trying to establish a chain of implication in between. Okay, so that is the nature of every mathematical proof. You have been using this for a long time. I assume all of you have taken algebra and trigonometry because those two are required for pre-calc, which is a prerequisite of this class. So that means you have already used the chain of implication already in theorem proving. You just do not usually see it expressed like this. Yep, pre-calc is gone. So what is it? What is it replaced by? Oh, okay. Okay. That's because of AB 1705. Yep. hmm Um, well, so what that results in doing is to guarantee that people who did not start with the necessary math background will never get to that level. That's the consequence. That is the result of the Assembly Bill 1705, which may or may not be the objective of that bill. That part I cannot interpret. That is trying to read into somebody's mind. But the logical fact is this is just making sure that people who could not take out calculus will never be able to take calculus. The funny thing, the really interesting part is AB 1705 is a community college only assembly bill. It does not affect CSUs or UCs. That is the truly amazing part of it, the whole thing. So if you go to a UC or a CSU, you can still take algebra, you can still take trigonometry, you can still take pre-calculus before you take calculus. It is only at a community college in California that you cannot if you declare your major as a STEM major. There are already people, there are already ways to kind of, let's just say, circumvent this requirement. Is we already have degrees that are basically pre-STEM degrees, so they are not actual STEM degrees, and therefore they are allowed to specify trig, algebra, pre-calc as a component of those things. So so that means people want to take who want to take algebra and trigonometry can declare that as a major first, get financial aid, and then once that degree is achieved, then change the program to a STEM program and continue. Yep, yep. In other words, the bill is useless. Yeah. All right. So getting back to what we are talking about here. Okay. So this is proof by contradiction. Using the corollary that we talked about, we are basically saying if phi is in fact a theorem, then psi should imply phi. Okay, so this is given the assumption that phi is a theorem, but this implies this. Okay, because of the corollary. And what we're ending with each component of the original implication is the negation of phi. In other words, we are negating the statement that we suspect is the theorem on both sides. Okay, so this implication is valid because of this thing here. So if this implication is also valid, then we are now saying, psi and not phi implies false because phi and not phi is guaranteed to be false. What can, if this implication is true, okay, if this implication is true, what can possibly be the value of this conjunction? In order for this implication to be true, and we already know the right-hand side is false, what is the value of the left-hand side? It has to be false. How do we know that? Yes. But we know that if you know the right-hand side of an implication is false, the implication itself is true, then the left-hand side has to be false. It's the truth table. You can just look it up. Okay? Yes, it is the truth table again. Okay? You can see how useful it is. Okay? It really is useful. So this is why we can validate proof by contradiction, which is basically saying if you negate the statement that you suspect is the theorem and then and it with everything that is axiomatically true, that conjunction should lead to false, hence contradiction. Is that okay? So I believe last Wednesday we also talked about how to use this to prove um, the pigeonhole principle. Okay, by negating the theorem itself, combine that with everything that is given to you, we arrived at a contradiction. We arrived at a statement that is false. So that means the pigeonhole principle itself has to be true. Okay, because we proved it by contradiction. We also had the sock example, tax sock from the drawer example, which is based on the same principle. So I'll be good so far with proof by contradiction. So now we have three things, right? So we have resolution, which is a mechanism. We have CNF, which is a format. Okay, we're basically just reformatting general Boolean expressions into a specific format called CNF so that resolution can be applied. And now we have the third component, which is proof by contradiction. So this really helps, to it jives with what we are doing today. Okay, we are reducing things until hopefully everything reduced to false because we are trying to apply proof by contradiction. So are we connecting the three main components before we move forward to present examples of using all three components to prove theorems? Yes. Mm-hmm. Yes. No, it's just straight up application of the resolution rule. Okay, so what does resolution look like? Instead of looking at me, you probably should be looking at either your own notes or the notes that I have written. So when people look at me, directly, when I ask a question, I go like, why are you looking at me? Because it's already written here and should be written in your own notes too. So this is resolution, and this is the example that we are going through. Do we see a resemblance? Do we see a match between this implication and resolution itself? We simply replace a bunch of Greek letters with variable names. And also the notations of the operators have changed a little bit. So are we doing okay so far? Okay, so are we getting all three components? Do we have any questions about each component before we go forward with an example? Yes. Is a resolution provides us the transformation. Because if this implication is always true, then we turn it into a rule in in Zeta. This is the only element in Zeta in this case. We only need one single rule, which makes, oh, which rule should we apply? Which makes the answer to that question rather easy because there's only one thing to consider. All right. So having understood all of those things, now we can go for an example. So the example, I'm not going to read the example. I'm just going to point out what we start off with. So in this case, what we are basically saying is this is given to be true. Don't ask me why. Okay. So that is, so once we convert this into a CNF, it becomes the C, the disjunctions of the CNF become elements of iota because they are all individually known to be true. Is that okay? So let's go ahead and work this out. Okay, you can also read the notes and find out how one way is, how to derive it in one way. But I'm just going to work it out today, assuming that we do not have the notes. So I'm going to work this out, again. But in my own notes here, I think Joplin may not be the best way to do this because I'm using the simplified notation. So let me start just a plain text editor and use that instead. All right, so this is just a regular text editor, and this is the reason why I choose to use the alternative way to represent and or not is simply that I can use a text editor to do everything instead of having to use Joplin to do it. So the original expression is not P or, and then we have a not, R implies Q, the whole thing, and P or T. All right, so this is what we start off with, and we want to turn this into a CNF. So the way we turn something into a CNF is semi-mechanical. So there are some cases where you kind of have to think a little bit about, oh, which rule should we apply at this point? But for the most part, at least at the beginning, it's really easy. The first thing is we get rid of all the implications. Okay, so to get rid of the implication in this case, it's not too difficult. Okay, because we simply look at the only implication here and say we negate the one side and then or the other side. This is just by the definition of implication. So now we look at this and go like, okay, all implications are gone. Let's go take a look at what else we can do. If you find that you can apply De Morgan's law, apply De Morgan's law. Okay, because De Morgan's law is applicable only because you have a negation of an and or a negation of an or. In CNF, the only thing you can negate is a single variable. So that means every time you see there's a chance to apply De Morgan's law, it is a good idea to apply that. Okay? And you can only apply De Morgan's law so many times because after you apply De Morgan's laws once, then you have gotten rid of the negation of an and or the negation of an or. Okay, now you might generate some sub cases of the negation of an and or the negation of an or, but if you apply that recursively, then you eventually will not have negation of and or negation of or. So we'll apply that. Okay, so we look at the first chance of applying De Morgan's law, which is the negation of this or over here. So now we preserve the parentheses. Okay, so in other words, I'm preserving the parentheses. So now we have not R and not Q on one side. P or T is maintained on the other side. So when I apply De Morgan's law, most of the time I do not also automatically apply cancellation of negation. So you can see there are two negations in front of the R. I just let it be for now, okay? Because I need to make sure that I can retrace my steps and check out if I got something wrong, where I got it wrong. Okay, so now we have now I simplify. This is R not Q. And because I prefer things to be in alphabetical order, so it is Q first before the R. P, Q, R. Yep, that's right. Okay, and then P or T at this point. Okay, and now I need to turn this, somehow I need to turn this into a CNF. So now not P is outside. So now I look at this. I have two ways to apply the distributive laws. Okay, the two distributive laws in Boolean algebra looks like this. It is always okay to restate those rules before you kind of see which one is applicable. So we can have A, B, or C. Once you distribute, this becomes A or C and B or C. The other one is A or B and C. This now becomes AC as a conjunction or BC as a conjunction. Okay, so now the question is, we know we have to apply one of these two. The question is, which one do we apply and where do we apply that? So you can see that, in this one, okay, if I somehow have a CNF to begin with, and the whole CNF is ORed with something, that is by itself, this will turn it into a CNF. So that's nice, okay? So that also means, I have this individual thing that is hanging out here that is going to be the C component here. So the objective is I want to turn this into a CNF first, which it is not. Well, it actually is right now. So you look at this and go like, how can this already be a CNF? It really is a CNF because not Q is a disjunctive element. It just doesn't look like one. R is also a disjunctive element. It just doesn't look like one. P or T definitely is a disjunctive, disjunction. So this entire thing, okay, let me highlight the portion. This entire thing is actually a CNF already. Some of you are going like, I don't think so. It just does not look like a or, okay? Not Q, how can that be a disjunction? If you're not convinced, fine. Are you convinced now? And same thing with R, okay? Are you now convinced that we have a sub, oh, not that, okay, there we go. So is everybody convinced that we have a C and F right here, just with a highlighted portion? Yes? Okay. So now we end up with the condition that is described on line 9 because we have a C and F on one side and the whole thing is ORed with a single variable or negation thereof. So now we just apply that distribution and say, okay, everybody gets to OR with not P. So now we just have to distribute the not P OR into, okay, let me highlight it. We now have to distribute this part into every one of these components. This one, then this one, and then this one. Okay. So now we just have to go like, oh, okay. So that means we have not P or not Q. Then we have not P or R. And then we have not P or T. And this is already correct. Okay, this is already a CNF, but we can simplify just a little bit because now we can say, okay, we can just do it like this, and this one is unique by itself, and that's done because the last one is true. How do we know it's true? Because not P or P itself is guaranteed to be true, and then true or T is also just going to be true. So basically, I just applied some simplification. If you want to see all the actual steps of the simplification, we can do that too. So the first step is to group these two together using the associative law. And then the second step is to look at that sub-expression and say, oh, that is just true. Okay, so simplify that to true. And then the third step is to say true or whatever is just going to be true. Oops. Um, yeah, backspace, backspace. That is going to be true. And then if you have blah 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 and true, the we can now simplify that to just everything without the and true because true is the identity of conjunction, just like one is the identity of multiplication. Yep. Line 5 already has a subcomponent that is a CNF. So when I said that, when I made that statement, I was referencing the highlighted portion. Yes. All right. So are we okay so far? Okay. All right. So everything that is on the projector is recorded. Okay. And I make sure that I have two mechanisms to do the recording today. Zoom is, oh, actually, I forgot to turn on the Zoom recording. So let me do that. So it's actually doubly recorded. But the OBS is recording for sure. So let me turn on the record to the cloud. Okay, so now Zoom is also recording and it's not screen sharing. Is it? Oh, somehow I lost the screen share on Zoom. Or is it on? Okay, so let me. Hmm? Well, I didn't have a chance to read text messages. The chat is empty, but I don't see the green highlight, but that may be. Nope, it's not on that side either. So I don't know whether it's actually recording the screen or not, or even broadcasting. It says it's broadcasting my desktop one. That's not what I want. Um, is the screen getting recorded? Is the screen being shared? And I can't hear the person who's online because I turned my volume all the way down. Okay, go ahead. Is it being is the screen share working? Okay. All right. Okay, so it was recording. It was working. Mm, okay. Alrighty. But OBS is definitely recording, so we definitely have a recording. All right. All right. So are we okay with this derivation, starting with some random-ish, expression and ending up with a CNF as conjunctive normal form? So this means, the iota, in this case, the set I or iota is going to be, okay, the usual suspects, okay, one, which is true, the negation of false, okay, so these are kind of known to be true, but we also have not P or not Q in iota, and then we also have not P or R in iota. This is the This is the membership of iota to begin with. Are we good so far? Are we relating given that this whole thing is psi, okay, which is everything that is given to you to be true, then the iota ends up to be the each component of the CNF. It's not the CNF itself that is in iota, it is the components of CNF that is in iota. Yes, because that's just not false is known to be true. Yeah, that's just things that we know about Boolean algebra, about the constants. All right, so now if we go back to the notes, okay, the notes actually has a slightly different and longer or more cumbersome derivation, but it arrives to the same conclusion. Okay, this one just expands unnecessarily using distribution, and then it simplifies, but it gets back to the same point. Okay, are we? Yep. hmm I think so. Because it's so much easier to type these. I just prefer to use the simplified notations as opposed to the math notation where I mean it means the same thing, but it just takes a lot longer to type, so there's no point in doing that. All right, so now we move on to um, we want to know convert the following. This is just an exercise. So proof by contradiction in this case, is we have done this already. So the exercise that we want to do in this case is now to use the same psi. Okay, this is the psi that we have worked with already. And this is a potential theorem. We don't know whether this phi is actually a theorem or not. We want to know if we know psi is true, can we guarantee that phi is also true? In other words, does psi implies phi in this case? That's what we want to find out. That's the whole purpose of propositional logic, is to prove theorems. So we cannot handle this directly because this does not work well with resolution because it does not look like a CNF to me. So the first thing we need to do is to negate phi first because we're using proof by contradiction. Proof by contradiction says you have to negate the expression that you want to find out whether it is a theorem or not. You have to negate it first. So when we negate not t implies p, the whole thing basically eventually simplifies to not t or not p. So let's do this by hand today. So let me go ahead and copy this so that we can just kind of work this out. So we know that phi is not t implies p. So the negation of phi is going to be the negation of not t implies p. And then we get rid of all the implications first. So this becomes not t or p. And then we simplify the not first. Okay, so it becomes just a t or p, but the whole thing is negated. Now we apply De Morgan's law. It becomes not t as one term and then not p as the other term. So I think this is also consistent with the result. Yep. hmm Do we have any questions about how I turn not phi into its own CNF? Okay. So what we want to know now, okay, so let me just type this in and then we'll work on the mechanism next. So what we want to know is whether psi and phi, not phi, whether this is false or not, okay? Because if this is false, that actually means that phi is a theorem based on what we talked about a little bit earlier. The validation of proof by contradiction that we talked about earlier says, okay, if you suspect phi is a theorem of psi, then you negate phi first, and then you use it to end with psi. If this conjunction is false, then we're all good. Okay, so that's what we want to do. But in this case, we already re-express psi as a CNF. Okay, so we're going to copy the CNF representing psi. And we also have not phi converted into a CNF as well. So we just concatenate the whole thing together. The first half, okay, let me use the mouse pointer. The first half here is psi. The second half here is not phi. They are ended together. We want to see if this is false, regardless of the values of the variables, whether this is false or not. So now we go like, okay, that's cool. So the way we perform resolution is it's easier to number these things, okay, one by one, so that we can see whether which two can resolve to another result here. So we just have to say 1, 2, 3, and 4. And now the question is, can we apply resolution? In other words, I'm asking out of the four expressions that we have, 1, 2, 3, and 4, do we have a situation where one of them has a variable that is not negated, and then the other one has the same variable but negated? The answer is nope, it is not applicable. Okay, resolution does not even apply once. So what does that mean? That means I cannot show that psi and not phi is false. And what does that mean in return? It means phi is not a theorem. It is that okay? So in this case, because no resolution step is applicable, or we cannot resolve to false, therefore phi is not a theorem. I have seen a lot of people making the conclusion that says phi is not true, but that is not true. Okay, there's no guarantee that phi is not true. We can only say that phi is not implied by psi. That's all we can say. We are not concerned about the value of phi itself. We're only concerned about whether psi is implying phi or not. So in this case, I presented a Boolean expression that is not implied by psi. And that is traditionally very difficult to do in proofs because it's easy to prove something that is a theorem, but if I give you something that is not a theorem, it is difficult to prove. Now you can prove by counter example and say that, oh yeah, this is not a theorem because I can find a counter example. Okay, but finding a counter example is not exactly a systematic way of proving something is not a theorem. This is very systematic. And what is nice about systematic in computer science? Why do we like things that are structured, systematic, repetitive, to the point that it is boring? Why do we like those things in computer science? Because we can automate, exactly. All right. So let's work with uh, phi prime, which is another proposed expression, and see whether it is a theorem or not. So in this case, phi prime, which is just another expression that we want to see whether it is a theorem or not of psi, is this. Okay, so we'll work on this one on the side like this. Okay, there we go. So this time we have phi prime being P implies not Q. So that means the first thing we need to do is to negate it. So the negation of phi prime is the negation of P implies not Q. All right. And now we want to convert not phi prime into a CNF. So now we look at this, and the first step is always to get rid of implication. So we have not P or not Q in this case, and then we can see that we can apply De Morgan's law. And remember what I said, if you see an opportunity to apply De Morgan's law, do it, okay? Because it is always valid to apply De Morgan's law in order to convert a Boolean expression into a CNF. So we apply De Morgan's law. So now we have not P and not Q. Then we apply the simplification. Double negation cancels out. So now we have P, Q as a CNF. So once again, we want to see if the conjunction between psi and the negation of phi prime in this case, we want to see if it is false or not. Okay, this is what we want, but we need to prove it. So now we concatenate psi. So psi is already worked out way earlier in today's lecture. So I'm just going to copy and paste it down here. Not phi prime is worked out over here. So we stash it right here. So once again, we have a concatenation between psi, which is consisting of these two disjunctions, and then we have the negation of the expression that we want to find out whether it's a theorem or not, and that would be this portion here. So are we still doing okay so far with these steps? Okay. So now we apply resolution until hopefully we get to false, or until the point where we cannot apply resolution to get a new result anymore. So once again, my personal method is to number each disjunction so I can refer to which two are, can resolve, and then the result becomes a new thing. So this is 4. There we go. All right. So I think this time we got, a few ways to do resolution. So before you get a hang of this, you can always do this very, very systematically. In other words, you start with 1, and then you see whether 1, 2 can resolve. In this case, 1, 2 cannot resolve. Then you move on to 1, 3, and you ask, can those two resolve? Yes, those two can resolve. So now we just say, okay, if those two can resolve, we end up with a 5. And then I just mentioned that it is the resolution between 1 and 3. And the result of the resolution is going to be just not Q. So I'm going to pause right here and see if you guys can see that the resolution between expression 1 and expression 3 results in expression 5. Are we good with that? We good? Okay. If you need more time to think about how to ask the question, you can also say that. So we all good? All right. Okay. So if I want to be super systematic, then I try to pair up 1 and 4, and those two can also resolve. Okay, so now I can say 1, 4 also resolve, and after the resolution, we get not P back. Okay, and some of you are going like, oh, I can see how we can resolve the whole thing now. Okay, I hope you can do that. But the computer cannot use what we call the eyeball algorithm and go like, yeah, I can see how those two can work out. So from the perspective of an algorithm, we're going to do the systematic, not necessarily the most efficient way, but it's the programmable way, okay? Which is to start with the second one and then try to pair up the second one with everything that is after that. So now we look at the second one and we look at the third one and say, can those two resolve? Yes. Okay. So expression 7 is the result of 2 and 3 resolving into just R. And now we look at 2 and 4 and ask, can those two resolve? Yep, those two can also resolve. 2, 4 cannot resolve. I take it back, sorry. That's my bad. And then 2, 5, okay, none of those can resolve anymore. So now we move on to 3. So we ask, can 3 and 4 resolve? No. Can 3 and 5 resolve? Yes. So now the question is, what do we get when we resolve 3 and 5? No, not 3 and 5, 3 and 6. Sorry, used the wrong number here. So 3 is P, 6 is not P. Those two can resolve. But after that is resolved, it looks like we got a empty tuple, but that is not the case. We actually just end up with false. Because the false is implied on both of these expressions. There's an implication of or 0 here, another or 0 here, another or 0 here, and another or 0 here. So that means when we resolve 3 and 6, we end up with 0 or false, which is really just false. So at this point, I can stop because everything that is implied, they're also ended together. In other words, the original conjunct CNF is only this long, but the current CNF that I have has one, two, three, four, five, six, seven, 8 terms in it. The last term of the conjunction being false means the whole thing is already false, which means, woohoo, we got it. Okay? It means the conjunction between what is given to you to be true and the negation of the expression that I suspect is a theorem is in fact a theorem because the conjunction resolves to false. Is that okay? Because this is the whole big picture. Okay, how do we start with some random psi, okay, things that are given to you to be true, some random expression that we suspect is a theorem, and go through the conversion to CNF, go through the resolution process. If we can end up with a false, then we are done with the proof. If we end up with a dead, if we end up with a dead end but not false itself, we are also done because in that case we can say, oh, phi earlier is not a theorem because there's no way we can derive false from that thing. So either way, we come to a conclusion. All right, so let me just kind of pause and see if there are any questions related to the whole process. Yep. So the way we see whether two of these expressions can be resolved is to ask the question of whether one contains a variable and then the other one contains the same variable but negated. But that really it goes back to resolution because we are just having very simple expressions for the Greek letter when we talked about resolution itself. Any other questions? Yep. Hmm. Yes. Because Yeah, because all of these are implied. So in other words, if I want to spell out the entire chain of implication, then we have this thing and this thing here implies this thing here. Okay? And whatever is implied can be folded into the conjunction itself without changing the meaning of the conjunction. In other words, if the original conjunction here is false to begin with, whatever the value is, if you end it with something that it implies, then it would still be workable. Okay, let me give you the general equation like that. So if A implies B, okay, then A equals to, I have to be careful here, AB, okay. So let's check out whether this is correct or not. Okay, A implies B implies A equals to AB. Okay, all right. So let's check this out. Okay, this is my claim. My claim tag claims that if A implies B, then A is true if and only if AB is true. So now can we prove this? And how do we do that? Yes. So let's do it with a truth table. Okay, so this is classic. Okay, so we got A, we got B. A can be false, false, true, true. While A is false, B can be false, true, false, true. So now we have A implies B. Okay, this is coming straight out of the truth table from week 1. So this is a true, true. This is the only false. This is true. Okay. So now we have A if and only if B, which means A, B are the same. So this is true. This is false. This is false and wait. You're correct. This is true. So now we look at A implies B implies A if and only if B if and only if AB. Okay, so we need one more component. We also need AB, A and B. That's even easier, okay, because this is false, false, and then true. Oh, this one I don't need, actually. Sorry, we don't need this one, but I'll just keep it around. Okay, now we want to know whether A implies B. The whole thing implies A if and only if AB. So we need A if we need A if and only if AB here. Okay. All right. What about this one? That's a true. That is a true. That is a false. And that is a true. There we go. All right. Finally, we have all the components. So let me express what we need to find out this time. A implies B, which is this column here. Does that imply A if and only if AB, which is the latest column here? And you can see that they are exactly the same. So that means it's going to be true, 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 true in this column. True, 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 and also true. Whew. Okay. So are we convinced? Are we convinced that A implies B as an expression implies A if and only if A and B? I sure hope so. Not just yet. Okay. But why is it important? Why is this proof important? It is important because it means every time we use resolution to generate a new term, we can end the new term into the original CNF without changing the value of the original CNF. So that means we are just stacking up additional terms, and all of them can be applied. We can apply resolution to any one, we can apply resolution between any two of the expressions in the conjunction. The result of the resolution can be added onto that CNF to increase the possibility of resolution. And then we keep doing this until we get to a dead end, which means we cannot apply resolution to end up with any new terms anymore, and yet we cannot get to false. Or we get to false and we're all done at that time too. All right. So now the question is, but Tech, I'm not really convinced that it is only a finite number of expressions that we can end up with through the use of resolution. Okay. So there are two ways to prove that there's only a finite number of expressions that you can end up with by repeatedly apply resolution. The first one is the most sensible proof, which is there's only so many expressions involving a finite number of variables. Okay, so think about three variables. Okay, how many expressions can you generate out of three variables? Okay, so I'm going to list it here. We got variable P, Q, and R, okay, just as an example. So now I want to look at all the possible expressions that involve the variables. So there are three possible ways for a variable to quote unquote appear in a disjunction. It's either itself that is not negated, it is negated, or it is missing entirely. Okay, so we look at the expressions that we can generate here. There are 27 of these. So the question is, can we do this in the systematic way? Yeah, absolutely. We can do it in a very, very systematic way. So we can say P, Q, R, not P, not Q, and not R. Is that okay so far? Okay. So now I do the typical lazy thing, copy and paste, and say for each one of these, um, there can be um, a P here, a P over here. Let me see. Okay, I have to be systematic, but still make it to make it make sense. Um, all right, so we have P, Q, R. mm, I don't want to use a graph representation because I can't really. Okay, this is we focus on. I can't. This one is not. Well, okay. I don't think I start off with a good approach here. Okay, so I'm changing my approach. So we have P, we have not P, and then we have P missing entirely. Okay, so P missing entirely is just false, in the uh, inside the parentheses. Is that okay? All right. So now we're done with considering P by itself. P, Q and R are both missing in this case. So now we say, okay, what about P, and then P can have a, whoops, where's my cursor here? So P or Q, not P can also be combined with a not or Q. This one can also be combined with a Q. And then we take a look at the negation. So we basically apply the same three over here. This is far easier to represent using a tree representation, but since I did not set up to use my tablet today, it's a little bit harder. Using a spreadsheet would actually be an easy way. Okay, go ahead. Now, okay, this is better. I just thought of it doing this way since I did not use my tablet today. So we go to my drive. Yeah, yeah, but so that's why it's not a very systematic way to generate all the possible ways, but this is going to be an easier way. So let's do this. Let's go do this in the spreadsheet. Create and share. Okay, and today's date 2025 0402. Okay, all right, this is easier. So we got three columns, P, Q, and R. Okay, so we're going to say P is missing entirely, P is not negated, and P is negated. And then each one is supposed to have 9 entries. So I screwed this up again. Okay, and then P can be present but not negated. 1, 2, 3, 4, 5, 6, 7, 8, 9. And then P can be negated. Okay, not P, not P, not P, not P, and not P. Okay, we need one more. There we go. Okay, so that's accounting for all the P's. So Q's is kind of the same thing, but it's nested. So that means, with Q, we can have no Q, Q is not negated, or Q is negated. And now we can use copy and paste. So copy, paste, and paste. Finally, R can be missing entirely, can be not negated, can also be negated. So now we do the self-replicating copy and paste, but I screwed up somewhere. Nope, I did not. Okay, there we go. So we got copy, paste, and one more paste. There we go. So now between columns A, B, and C, if you look at each row, it is representing a disjunction that somehow involves the three variables P, Q, R. Okay? If you are not convinced about that, let's go ahead and see if I can use, I think it's called concatenate. Okay. Oh, did I have a typo? Concatenate. Yeah, I did have a typo. So we concatenate um, this thing. Yeah, there's no join unfortunately, so I have to kind of do it the long way. Q2 plus uh, plus and then C. What is it? Q. B. It's supposed to be B. That's right. And then finally we have C2. There we go. Yay! And now I just have to do this. All right. Well, now we have all the 27. It's far easier to look at it as a tree, but I did not set up myself to draw anything today. So this is kind of like a tree, but it doesn't look like a tree. Is everybody convinced that this is actually a tree? Okay. So if I were to look at this as a tree, this is the first level branch. Okay, this is the first branch from the first level. This is the second branch of the first level, and this is the third branch from the first level. From the first branch, this is the first sub branch of the second level. This is the second sub branch of the second level. This is the third sub branch of the second level. This is the third branch along the tree, depth wise. The first one of the third, the second one of the third, and also the third one of the third, and so on. Okay. The point is it finite? And given 5 variables, how big would that table is? I'm not going to draw that table. No. Hmm? Nope. Okay. You guys have already spoken a few of the ways to express something to the power of something, but they're both wrong. Okay. So what is the third one? Each time we have a branch, each level of the tree, each branch out has a branching factor of 3. And then the number of levels is controlled by the number of variables. So if we have 5 variables, then we have a depth of 5 of that tree. Each level has a branch out of 3. So how many leaves do I have in that case with 5 variables? Is 3 to the power of 5. So 3 to the power of 5 is a rather large number. Okay, so let me kind of display that. 3 to the power of 5 is, oh, okay, not even that big of a number, 243, but I'm not going to do that by hand. Okay, but the question is it finite? Yes. Okay, so that means the worst case scenario, okay, you just have to apply resolution at the most, absolute at the most, 243 times, then you can prove whether something is a theorem or not. For sure. Yes. Hmm? You hope what is not on the test? No. I would never ask you guys to do something that mundane. Huh? Yes. That is how big the haystack is. But because resolution has its own restrictions, right? So that means the actual number of possible resolution should be far less than 243. Yep. So even with 5 variables, we are looking at a very manageable number of times that we have to apply resolution. But resolution at this level is very mechanical. You are really just looking at an expression and ask, okay, between this disjunction and this disjunction here, does and then you look at all the possible variables and you ask, okay, if I look at variable p, is it not negated in one and negated on the other one? Nope. What about q? Okay. What about r? What about r? And what about t? It's a very mechanical process. So I have actually written the code in JavaScript to do all this, and that's how I can generate the key in the second exam. Huh? Well, JavaScript compared to Java or C++ is interesting to debug because you can have something that is not even entirely syntactically correct. Um, if you don't step on that line of code, it will never complain about it. It has no type checking, which means if you accidentally use a variable incorrectly and the types are not consistent, it doesn't complain about it. It goes like, well, looks like you know what you're doing. Fine, we'll just do it. And the worst part of JavaScript is it will do type coercion. Like, it depends on the context. You can give it an empty string in the context of a Boolean. It goes like, oh, I know what you intend to do. Empty string means false. Whether it means false or not, it will be automatically done. You can also give it an empty array or something like that. And in the context of a Boolean, it goes like, I see that you want to derive a Boolean value out of something that is not Boolean. I'll do it for you. This is also why we have that bug in Canvas. Okay, some of you, or those of you who took CISP 310 from me, you will notice that with calculated answers, if the answer is a zero, you put in a zero, Canvas will complain that you did not answer the question at all. So what it is doing is it is not comparing, it's not checking whether the field is an empty string. It just takes whatever is in that field and stick it into a Boolean context. And if the Boolean interpretation of that thing is false, then it comes back and say, oh, you did not answer this question. And zero, which is a non-empty string, in the Boolean context can be interpreted as false. In JavaScript, there is no differentiation between zero as a numerical value and the string zero. Double quote zero and double quote, they are the same. The only time it would do something differently is dependent on the context. So you can end up with bugs like this. I told Canvas about the bug. I told Canvas about the symptom. I told Canvas about what most likely is the cause of the problem. And that was when we first started to use Canvas, how many years ago? And it is still not fixed. And I consider myself a rather sloppy and lazy person. So where does that put in structure? Which makes Canvas. It means, if I was a boss in that company, there will be people getting fired. Alrighty. So we are done with today's lecture. I'll see you guys next Monday. But please, please spend some time to review the material. Alrighty. The term river spider was coined because it was originally intended as an automatic crawler that bypasses all the authentication. Yeah, that was the intention originally. Hmm